Hey, so today I wanted to talk about essentially slides 11 to 17 on the thermodynamics slides and going over a couple topics that we're talking about in class. One is just the equation Q equals mc delta T. So the energy equals the mass of what's being heated times C, which is specific heat of the substance being heated, times the change in temperature involved, and that was the cat. So you might have a question, how many joules are required to heat 200 with a decimal, so 3 sig figs, grams of aluminum from 25.0 degrees Celsius to 125 degrees Celsius? The heat capacity of aluminum is 0.897 joules per gram degree Celsius. So first thing is figure out, what are your givens basically? So we have Q. Well, we don't know what Q is at this point. That's what we're solving for. Because it's asking how many joules, and that will be Q. C is the specific heat, and that's how much it heats per gram degree Celsius, or how much energy it takes to heat it per gram degree Celsius, and that number is 0.897 joules per gram degree Celsius. Now the mass, and that's the mass of what is getting heated, is 200 grams. And finally, delta T is the change in the temperature, and again, it's heating from 25 to 125, so the difference there is 100 degrees. So 100 degrees Celsius. Then plug into the equation. So oops, Q equals 200 times, so there's your mass, times 0.97 joules per gram degree Celsius, times the change in temperature, 100 degrees. Degrees Celsius will cancel, grams will cancel, and we'll be left with joules. And when you run the numbers, you get Q equals 17,900 joules, 3 sig figs, so 3 sig figs here. Okay, now there are also some problems that instead of looking at change in temperature, we're actually looking at change in state. And you have to do those a little bit differently. And for example, for water, there's a couple states that can change. Water can go from liquid to solid or solid to liquid, and it can also go from liquid to gas or gas to liquid. Now, the heat of fusion of water, and that's the amount of energy it takes basically to take ice and turn it into water, is 6.01 kilojoules for every mole of water. And remember, a mole is about 18 grams of water. Okay, then the heat of vaporization of water is approximately 40.67 kilojoules per mole. So it actually takes a lot more energy, and that's how much energy it takes to convert water, liquid, into steam. So again, a much bigger number, 50.67. Now, if you're going the other way, you're actually giving off heat. So when you freeze water and turn it into ice, you actually are giving off. So there would be a negative sign here, 6.01 kilojoules per mole. And if you take water and condense it, or steam and condense it, it's going to be a negative 40.67 kilojoules per mole. So there might be a question, determine the heat given off when 90 with a decimal grams of steam is condensed at 100 degrees Celsius, again with a decimal, and then cooled to 50 degrees Celsius. So there's actually two parts to this problem. One of them is converting to steam, or the steam into liquid water. And for that part, we actually have to use dimensional analysis. And first off, we have 90 grams of water, which is a gas at this point, it's steam, and then convert that to moles. So 1 mole of water is 18.015 grams of water. And again, both of those are gases. And once you've converted it to moles, we had from the previous slide there, you saw that there were negative 40.67 kilojoules. So that many kilojoules is released when it turns into a liquid, liquid water from the steam. So negative 40.67 kilojoules are released for every mole of water. And again, that will then make it into liquid water. And then you have 1,000 joules per kilojoule. And when you run the numbers, you get negative 203,181 joules. Now you also have the change in temperature. So once you have converted to liquid water, you need to cool it from 100 degrees down to 50 degrees Celsius. So there we have, Q equals mc delta T. M is our 90 grams of water. C is 4.18 joules per gram degree Celsius. And delta T is negative 50 degrees Celsius. Again, we're cooling it, so we're actually giving off heat. Plug those numbers in, and we end up with negative 18,810 joules. Then you simply add those two numbers together. So negative 18,810 joules plus negative 203,181 joules is negative 221,991 joules, or rounding negative 220 kilojoules. Okay, so that's a type of problem that you might see. Now, we also have some terms. So enthalpy is the heat content of a system at constant pressure, and it's used to measure energy changes in reactions. So in the previous case, we were looking at a substance and either heating it or cooling it or changing the state of the substance. Now, we're going to talk about when we have actually reactions and when we have change in energy in reactions. And there's a couple ways you can look at it. And today we're just going to look kind of big picture, and then we'll go into bonds later on, probably next week. So the standard unit here is kilojoules per mole. And like we said last week, negative delta H is exotherm. It's giving off heat. You're left with less heat in the system than there used to be. So the products have less potential energy than the reactants had. And then plus delta H is endothermic. Energy is being brought into the substances, and you've gained energy. So the products have more energy stored within them than the reactants. And delta H is the change in heat from a reaction or a phase change. In this case, we're going to be actually talking about reactions. And so we have a formula here where the change in heat for a reaction is the sum of the heat of the products minus the sum of the heat of the reactants. So I have two examples to show. And to get the amount of energy, there are tables. So, there's printed tables such as this. And actually for IB, they actually give you we have this chemistry data booklet here. And when you look in the chemistry data booklet, sections 12 has selected compounds, and it gives you a bunch of values here in the data booklet. So this would be kind of how you'd go about doing that. So first off, you do want to balance the equation. It has to be balanced. Then determine the heat of formation values for all the substances involved. For atoms and molecules of the same element, though, delta H of formation is 0 kilojoules per mole. So if you have like O2 or just sodium metal or something like that, and it's not bonded to anything other than the element itself, then it's 0 kilojoules per mole. All other situations, so like H2O or CO2, something like that, will have values. And so you can look up those values in the table. Or in most cases for you, it will be in the data booklet. So for example, if we had a reaction, and this one I think is already balanced here, H2 plus N2 goes to NH3. When we balance it, we get 3H2 plus N2 reacts to yield 2 moles of NH3. Then, looking up the values, again, H2 is 0 because it's bonded to itself. N2 is 0 kilojoules per mole. And then NH3, when you look the value up, it's negative 46.11 kilojoules per mole. Then we need to take the sum of the products. Well, here there's only one product, but there's 2 moles of it. So 2 moles times negative 46.11 kilojoules per mole. Then subtract from that the reactants. So minus then 3 moles times 0 kilojoules per mole, minus again 1 mole times 0 kilojoules per mole. Well, these are both 0 kilojoules per mole, so they all kind of cancel out. And we're just left with this, or 2 times negative 46.11, or 92.22 kilojoules negative. And so what that's saying is that when this reaction occurs, you're giving off a bunch of energy here, a little over 92 kilojoules of energy, so the surroundings will get hot. That would be an exothermic reaction. So another example could be C2H4 plus O2 reacts to yield CO2 plus H2O. And let's assume they're all gases. And it does matter if they're gases or liquids, the values will be different. So first off, balance the reaction. And to do that, there's 2 carbons here, so you'll need a 2 there. And there's 4 hydrogens and 2 oxygens, so you'll need a 2 here. So that would be our balance reaction. Then again, the formula here is delta H of the reaction equals the sum of the H of the products minus the sum of the H of the reactants. So when we do that out again, here are the products. So we're going to have 2 moles there times the value for CO2 is negative 393.5 kilojoules per mole. Then plus 2 moles times the value for gas here for water is negative 241.8 kilojoules per mole. And then, let me note that, minus 1 mole times 52.0 kilojoules per mole. And then there's also a water or an oxygen in here. I didn't put this in the equation because, again, oxygen it's O2, it's 0, that will cancel out. So this is the part that really matters. So then the delta H of the reaction, when you do the math out, is negative 1,322 kilojoules. Okay, so it generates a heck of a lot of heat, which kind of makes sense because these hydrocarbons like this are used for energy, and they're used to power things. They're used to run your cars, stuff like that. This is a pretty small molecule for that, but again, these are often fuel molecules. Okay, we'll talk about bond enthalpies later. So I think at this point, that's what we have. And so it's over here. That's what I'm trying to hit is the exit, and then we want to stop this. Right?